Hello, Mr. Betts here. I want to take a look at a few examples using the integral test for convergence. And really, this is a test for convergence or divergence as long as conditions are met. So the idea here is we want to match up this series with a function that's going to match term for term. And this is pretty straightforward. Essentially, what we're going to do is we're going to replace the n with x, and we're going to say, okay, if f of x is 1 over x, then f of x and the series are going to be the same for integer values of x. So what we're going to look at here is the integral from 1, and I'm going to choose 1 because that's where n starts here, to infinity of 1 over x dx. And so to evaluate this, we're going to use an improper integral. So as an improper integral, we're going to use a limit. So I'm going to say the limit as, say, c approaches infinity of the integral from 1 to c of 1 over x dx. So remember, with an improper integral, we have to make this essentially a constant, but then look at what happens as that constant approaches infinity. So this, evaluating with the antiderivative, is going to be the limit as c approaches infinity of the natural log of the absolute value of x evaluated from 1 to c, which is going to be the limit as c approaches infinity of the natural log of c minus the natural log of 1. Well, the natural log of 1 is 0. The natural log of c, as c approaches infinity, as c gets really big, the natural log of c also gets really big. It does grow very slowly, but it is infinite. So this limit does approach infinity, so that limit diverges. So since the limit diverges for this integral, then that means that the series also diverges. So same idea in the second example. So first thing we're going to do is match that up with a function. F of x is going to be 1 over x squared. So what we want to evaluate then is the integral from 1 to infinity of 1 over x squared dx. So again, with an improper integral, our first step is to rewrite it as a limit. I'm going to just use c again. So limit as c approaches infinity of 1 to c, the integral from 1 to c. That x squared I'm going to rewrite as x to the negative 2. And I'm going to, I write it like that for the purpose of taking the antiderivative. So the antiderivative of x to the negative 2, we increase the power by 1. So x to the negative 1 divided by negative 1. So it's going to be negative 1 over x. And we're evaluating that from 1 to c. So that is going to be the limit as c approaches infinity of negative 1 over c minus negative 1 over 1. And as c approaches infinity, if we're dividing by a number that's getting really big, that's going to approach 0. So we get 0 minus negative 1, which is positive 1. It actually doesn't matter what the sum is, at least for the purpose of answering this question. The question just says, does the series converge or diverge? Well, the integral converges. And so the integral test says that the integral and the series will either both converge or diverge. So since the integral converges, then the sum is also going to converge. It's really important for me to point out that we're not actually looking for what the sum is. That's a problem for a future math class. Right now, we just want to know, does the series converge or does it diverge? So this sum is going to be a finite sum. This example here, we don't actually need to use the integral test. So if we think about what's happening here as n is getting bigger, so as the terms get bigger, n squared is getting even bigger. So the limit of the terms as n approaches infinity is infinite. And so the nth term test for divergence tells us that this series is going to diverge. So the integral test does not even apply here. This is not a decreasing function. The integral test only applies for positive decreasing functions, and this is not a decreasing function, it's an increasing function. However, even though the integral test doesn't apply here, we know that the series is going to diverge because of the nth term test for divergence. Let me write that down here. So if the terms don't approach zero, then the series has to diverge. This one, as n gets bigger, these terms are approaching zero. So the terms themselves approach zero, which means that the series could converge. So we're going to use the integral test. So f of x here is going to be 1 over the square root of x. So what we're looking at here is the integral from 1 to infinity of 1 over square root of x dx. So again, this is an improper integral. So we're going to look at the limit as c approaches infinity of the integral from 1 to c. I'm going to write that as x to the negative 1/2 dx. And so evaluating that, the antiderivative of x to the negative 1/2 is x to the positive 1/2 divided by 1/2, so times 2. So that would be 2 square root of x, and that's evaluated from 1 to c. So that is going to be the limit as c approaches infinity of 2 square root of c minus 2 square root of 1. Well, as c approaches infinity, the square root of c also approaches infinity. So this limit diverges. It approaches infinity. So the limit does not exist, or it diverges, or is infinite. You could say that a few different ways. And because of that, the series itself also diverges. So this sum is going to be an infinite sum. Okay, integral test here. So as n gets bigger, the terms are getting smaller and closer to zero. So the integral test does apply because it's a positive decreasing function, with f of x being 1 over the square root of x cubed. So we're looking at the integral from 1 to infinity of 1 over x cubed, the square root of x cubed. And so we rewrite that as a limit. And the 1 over the square root of x cubed, I'm going to rewrite as x to the negative 3/2 power. That way I can use the power rule on it. So this is going to be the limit as c approaches infinity of, if we increase the power by 1, that's going to be x to the negative 1/2, dividing by the new power, that's going to be times negative 2. So we get negative 2 over the square root of x, evaluated from 1 to c, which is going to be negative 2 over the square root of c minus negative 2 over the square root of 1. So as c approaches infinity, the denominator here is getting really big, and so we're going to get 0 for that first term, and then plus 2 for the second term. So this limit, which represents the infinite area, or the area of the improper integral, is finite. It converges, which means that the series is also going to converge. Again, it doesn't matter that the sum is 2. That sum could be seen as an approximation for the sum of the series, but the value of this integral right here, being finite, just tells us that this is going to be a finite sum, but it doesn't tell us what that sum is. It just tells us that it's going to converge to some finite number. Okay, last example. So This is another one where as n gets bigger, the denominator gets smaller. So as n increases, the terms are decreasing. So the integral test is going to apply using the function 1 over the cube root of x squared. So the integral that we're going to be looking at is the integral from 1 to infinity of 1 over the cube root of x squared dx, rewriting that as a limit. I'm going to write this as x to the negative 2/3 power. And so taking the antiderivative here, it's going to be x to the positive 1/3 power. Okay, so we need to leave the limit on there. So x to the 1/3 power divided by 1/3 would be times 3, evaluated from 1 to c. So that's going to be the limit as c approaches infinity of 3c to the 1/3 minus 3, 1 to the 1/3, or just 3. So on this one, as c gets really big, c to the 1/3 power also gets really big, and this limit diverges, approaches infinity, which tells us that this sum is going to diverge. So this sum is going to be infinite if we add enough terms, which we are adding infinitely many terms, so we will be. And there you have it, the integral test.